organizar una agenda, una familia, a unos peques que hoy nos acompañan además y que nos hace muchísima ilusión poder acercarnos más allá de ese WhatsApp tan vivo que tenemos, pero esto creo que es muy importante, acercarnos entre todos y trabajar en el mismo camino todos juntos. Entonces, ahora nuestra compañera Nuria va a hacer una presentación sobre lo que vamos a poder escuchar hoy aquí y luego habrá una serie de preguntas para poder resolver todo lo que vaya surgiendo. Y nada, solamente quería daros las gracias a todos. Un abrazo.
Hola, buenas. Bueno, bienvenidos a todos a esta tarde aquí en el Hospital Niño Jesús. Yo soy Nuria Lamagrande, que soy neuropediatra de aquí del hospital. Y nada, esta tarde vamos a hablar un poco del KCNQ2. Va empezando hablando Sara Weckhuysen del Instituto Molecular de Amberes. Luego después el doctor Antonio Gil Nájel del Hospital Ruber Internacional. Luego vendrá Marta García Fernández, neurofisióloga de aquí del hospital, y luego hablaré yo un poquito. Pues nada, Sara, si quieres, nada, bienvenidos a todos y espero que os guste mucho todo.
Muchas gracias por la invitación. Estoy contentísima de estar aquí. Primero, lo siento muchísimo, pero mi español no es como antes, entonces tengo que hacer la presentación en inglés, pero lo entiendo todavía muy bien, entonces si habéis preguntas lo podéis hacer en español y pruebo de contestar en español. So, I'm Sarah Weckhuysen. It goes easier in English for me. I'm actually an adult neurologist, but I have a specific interest in genetic epilepsies and specifically in KCNQ2. And for the talk of today, I tried to make a little bit of mix, starting, and I have it on my next slide, I think, just starting with a short summary with something that you probably all know, and that is that there is a lot of similarities between people or children and adults with KCNQ2 mutations, but also some differences, and this depends on the type of mutation the children have. So I'll discuss this a little bit. Then I give you a little bit an update on which treatments that we have now for KCNQ2 related disorders, which treatments are in development as far as I know of, and I don't probably know everything. And related to this, I give you a little bit a summary of what type of clinical work we do in our team in Antwerp in Belgium. And then to start, and that's also why this is a talk of the title of my talk, I give you a short summary of some research that was done in a European consortium that tried to identify new treatments for KCNQ2 related mutations. Okay, so I don't think I have to explain you what KCNQ2 is, but still, just as a reminder, so the neurons in our brain, they connect or they talk to each other through electric signals, and these electric signals, they're generated or made by channels in our brain that are permeable for charged elements. And one of these channels is the potassium channel KCNQ2. And actually, it is very important to reduce the electric activity, to stop electric spikes or electric signals in the neurons, and to make sure that they don't become electrically active when they don't have to. So it's a very important. It's like a break in our cell system or in our brain. And because it's so important in electric signaling in the brain, it's not unsurprising that if something goes wrong with this channel, it can really lead to problems. And over the years, we have seen that there's different types of problems with the channel that lead to different types of problems in human beings or in humans. So it's possible that the channel doesn't work enough, and we call this loss of function mutations. And then you have seizures or epilepsy as a neonate. When it even works less than just a little bit, you get even more problems. You don't only have neonatal seizures, but also neurodevelopmental problems. Or it's also possible that the channel is always open, that it works too much, And this mostly gives rise to people or children that have neurodevelopmental problems and sometimes later onset epilepsy. I often show this timeline just to illustrate for how long we know these disorders yet. This 94 here in the beginning, that's the first epilepsy gene that was described. And then actually KCNQ2 and also KCNQ3 that were one of the earliest epilepsy genes identified. At that time in big families with neonatal seizures, something that we call now self-limited familial neonatal epilepsy. And then it took until 2012 until we identified that some mutations in the gene not only lead to neonatal seizures but also neurodevelopmental problems. And some years later we saw that some of the children don't even have neonatal seizures. They only have neurodevelopmental problems and later onset seizures. This is a little bit of numbers to know how frequent it is. It's a rare disorder, it's a genetic disorder, but it's actually not so infrequent. So from a big cohort study in, I always forget, is it Ireland or Scotland? But it's 1 in 17,000 people that are born have a mutation in KCNQ2. This is not so little. And then if you look at the more severe forms, there's an estimation that says 1 in 3 per 100,000 people have this disorder. So I don't know how many people there are in Spain, but you can make the calculation how many children potentially or people that we think live in Spain with the disorder. You can also only just focus on children that are born and that have epilepsy because of a genetic cause, and then it's 1 in 3. So that's quite significant. So it's not so infrequent. And so many mutations have been described over the years and they have been tested. So it's not so easy to test something that goes wrong in the brain. So what people do is that they take the channel and they put it into a cell, they put it in a dish and they test how good the channel works. And what I have seen, and that is what I shown you before, is that there's different types of mutations, different types of problems with the channel, and then you get different types of disorders. Very shortly, because you probably all know this, so the very first thing were these big families with children with neonatal seizures. They go away after a few weeks, a few months. EEG is normal, the MRI, if you do imaging of the brain, it's normal, and these children do totally well. And then, as I said, 2012, so a little bit similar, so children also with neonatal seizures, very often they have multiple seizures from the beginning, from the start when they are born, but the EEG is not normal. Typically, this goes the wrong way. So this is how the typical EEG of children with the more severe form of the disorder looks like. You have this burst of activity and then you have a silencing, a suppression. And these are typically children that do have neurodevelopmental problems. And then they can have a range of other comorbidities that you probably are very aware of. Many of sleep problems, they can have behavioral problems, gastrointestinal problems. So this is obviously a very big burden for families. These mutations, they have been tested, as said, not in the brain because that's difficult to do. And they know if you have this just neonatal seizures and you test how the channel works, that is one of the 2 copies that we have. We always, in our DNA, we have a copy from the mother and one from the father, and one of them doesn't work good enough. So you see there's less current through the channel. That is what happens if you have this neonatal seizures and then a normal development. And if this break, I told you, these KCNQ2 channels, they are like the brake on the neurons, so they reduce the electric signals in the brain. If the brake doesn't work too much, you get too much activity in your brain, too much activity of the neurons, and that's what epilepsy is. They become active when they shouldn't. In the more severe form, where children have neonatal seizures and they're neurodevelopmental, or also these mutations have been tested in a cell, many of them, and what they saw is that there's even less current through the channel. So although they have a good copy of the mother or the father, apparently this bad copy, it interferes with the functioning of the good copy. So you have a more than 50% loss of the current through the channel. And this is something we call them dominant negative mutations. So they have even a negative effect on the good copy of the gene. And so also here, the brake doesn't work almost at all anymore. Your nerve cells even become more hyperexcitable, to such extent that you don't always only have epilepsy, but it also interferes with the development of the neurons. And that's when we see these neurodevelopmental problems. And then last but not least, and maybe there's some families that recognize some of these mutations, there's more of them, but these are the most important ones. Some mutations in KCNQ2, it's a minority, but they don't lead to a loss of the current, but the channels are constantly open, so there's too much current. And these are the children that typically they don't have neonatal seizures. Sometimes when they're born, they have these jittery movements, what we call myoclonus, but they do have neurodevelopmental problems. Some have later onset epilepsy, and typically in the most typical forms, if you do an EEG at night during sleep, you do see epileptic activity. So as I said, then there's one of the two copies that works too much, and we call this the gain of function variance. So now the brake, it works too much, so your nerve cells become less excitable, they function less. It's quite logic to see that this leads to neurodevelopmental problems. It's not yet totally clear why this leads to epilepsy. Probably it's some compensation mechanism. So this is a little bit the summary. Right? So you see KCNQ2 related disorder, it's not one disorder, there's a lot of similarity, but it's actually a whole spectrum. And depending how much the channel still works, it will define for a great extent what the problems what kind of problems children will have. This also means if you want to talk about prognosis and what to expect, it's very important to know what the variant in your child, what it does exactly. And it is a fact that if you look at children with the same variant, in general, they have the same kind of problems. And I say in general, not a single child is the same. We're all different. But it helps to look at other children or other adults that have the same mutations. Look into literature, talk to your medical doctor. There is one registry that you can find online. It's not really up to date, but sometimes you can find your child's mutations in there. Or you can contact and reach out to people in the field. And for example, I'm always happy to see or to look whether the variant in a specific child, it has been described before. In general, if you have a gain of function variant here, so people don't have gain of function variants, don't have neonatal seizures, it's quite easy to predict the type of variant. Sometimes it can be more difficult if a child is born and you make the genetic diagnosis. What will the prognosis be? Will there be neurodevelopmental, or is it just neonatal seizures and that's it? Especially when there are no other children with the same variant, then it can be very tricky to predict this. And ideally, we can do functional testing for all the variants, but this is very difficult. And until now, there's no very high throughput system that you can put in the lab and then you can test every single variant in a gene as KCNQ2. So one of the project that we have in our group running is to try to see if we look at the information of a lot of people with KCNQ2 related disorder, can we look at features, clinical features that are present from the start, that you can predict whether or not it's just neonatal seizures or will it be neonatal seizures and probably neurodevelopmental problems too. And for this, we collect information a little bit like a natural history study, and I understand that this is also something that you're setting up in Spain. Like, can we learn from the children that are born already and and that grew up, what particular features when they were born can tell us something about what will happen in the future. And this is very preliminary, so this is not the final thing. I'm just going to show you what clinical information we have on, at this moment, 180 individuals with KCNQ2 mutations, all types of KCNQ2 mutations, and we asked anonymously what was the age when the seizure started, what were the type of seizures at the beginning, how frequent were they at the beginning, what did the first MRI show, the first EEG, and when you did the clinical exam, the medical doctor, neonatologist, what were the signs, what did they find? And then later in life, we asked them what was the degree of intellectual disability, were they developing totally normal, the children, did they have mild, moderate, severe or profound disabilities. This is not a perfect study. We go back in the old records, not all information is documented very well, but I think what you, for example, immediately see that there's not a single thing or a single sign that can tell you if you have, for example, seizures in day 1, then this will be the results. That's not possible. But what you maybe can appreciate is, for example, if you already have seizures from the first day when you were born, then the chance is very high that there are problems with development. If you have tonic seizures, only the tonic seizures at the beginning where children stiffen very much, the chance is high that you have neurodevelopmental problems later. If you have so many seizures that it's really impossible to count them, so continuously, the chance is very high that there will be neurodevelopmental problems later. The same also when you look at the brain MRI. If there's abnormalities, there is a high chance of problems later in life. The other way around, if MRI is normal, it's difficult to predict what will happen later in life. We looked also at EEG, we looked at clinical signs in the beginning, and we believe that if we put all these things together, we can hopefully build a score. So if we can learn from children that were born and take all the clinical data together, that we can make a score. If you add up X and A and Z, then you can predict. You have to be extra careful and check neurodevelopment carefully, or you can be very confident. You can tell parents the chance is very high that your child will develop normally. All these items here separately, they're very straightforward. I think many clinicians will think, if the EEG shows a burst suppression pattern from the beginning, that's not a good sign. It's just that it's not an absolute finding. Sometimes some of these children do develop well. So we hope that by combining them and with gathering a lot of information from a lot of children, that we will be able to build this prediction score better. So that's the first thing that we're trying to do. Then what about treatment? What do we now know at this moment about the treatment, the best treatment available for children with KCNQ2 related disorders? And this is a little bit why I started with the introduction that you probably already knew, is that there's two types of mutations. Sometimes the channel doesn't work enough and sometimes it works too much. And probably these two types, they need different types of treatments. In one you have to activate the channel more, and the other you have to block the channel more. And you might have heard that we had actually a drug, retigabine or ezogabine, that was a potassium KCNQ2 channel opener, an activator. So it helps for the children where the channel doesn't work too much, the children with loss of function mutations. It was a drug that we used for epilepsy. It came to the market in 2011, but unfortunately in 2017 it was taken off the market. And maybe some of the people with older children might have taken retigabine in the past, but it's not available anymore. That said, many children were taking this drug, and we know that at least for some of them it really helped, at least for the seizures. Many parents also said that my child is more alert, he's more awake, or she, although there were never really good clinical trials to prove this. But it was a very promising drug. Some of you also might know that there was actually until last year a clinical trial. There was a company, Xenon, who bought the compound from the other company. They made a formulation that was easy to give for children. And they started a trial specifically in patients with KCNQ2 mutations. They included children between the age of 1 month and 6 years. And they asked children to have at least 4 seizures a month. And this was a little bit a problem. Because if I look a little bit maybe here in the room, and if I ask how many children still have 4 seizures a month, I think it's probably a minority, or not that many. There's 2 things. At first, they wanted the children to have a lot of seizures, and only until 6 years. And this made it so difficult to recruit patients that they stopped the trial in 23, so last year. So it was not because they thought it was not effective, just they couldn't find enough children to include in the trial. And that's a little bit a problem because seizures, or an effect of seizures, it's easy to count. You give a drug and you see whether it works. If a company has to develop a trial to look whether there's an improvement in development, you need a much longer trials, and it's much more difficult to quantify. What they said as not an excuse, because it's also true, is they have another drug in their pipeline. They're developing another molecule that activates the potassium channels, the KCNQ2 channels. And they're having trials, a clinical trial, and I'll talk about it in the next slide now, that they include patients from 12 years onwards. And they say, we're sure this is going to work, we bring it to the market eventually, and then it will be available for children with KCNQ2 related disorders. But obviously it's in development for epilepsy. So this is the trial. So now there are 2 companies that work on new potassium channel or KCNQ2 openers. So there's, again, the same company, Xenon. They have another compound. They always give it a name. And now they have an official name, azetukalner. They finished already 1 trial. So it was for epilepsy in adult patients. So without KCNQ2 mutations, just all adult patients with epilepsy. Also here, they had to have 4 seizures a month. It's a medication that you only have to take once per day, so that's nice. And they showed in this trial that in the highest dose, 50% of the people with epilepsy had less seizures. And side effects were, there were not too many side effects. Some dizziness, sleepiness, fatigue. So they now have a bigger trial with even more people, began mostly in adults with focal epilepsy, but also in children or young adults from 12 years and onwards with generalized tonic-clonic seizures. For all these trials, people have to have a minimum of seizures per month. So I think that not that many children with KCNQ2 mutation could enter in these trials, especially if they're young. But obviously, hopefully, when it comes to the market, it can be used in children with KCNQ2 mutations. Although at the beginning, it will be probably off-label. What does that mean? That it's approved and reimbursed for epilepsy, maybe in adult patients, but not yet in young patients. There's another company, Biohaven. They're maybe a little bit behind in the sense they just finished a phase 1 study in healthy individuals. So they give the drug to healthy individuals to see whether it's safe, and it seemed to be safe, also 1 time per day. And now they have 2 studies going on also in Europe, but again for adult patients with epilepsy, a minimum of 4 seizures per month. So if there's any adults, most children or people I see here are not at the adult age, I think. But if there are people with enough seizures, they can enter the trial, but I believe there will not be that many candidates. how many years? So they have to be, so wait, can I show? Yeah. If they have focal onset seizures, so there you have two big types of seizures. Seizures that start in one part of the brain. I think most of the children with KCNQ2 related disorders later in life, they have focal onset seizures also, but then they have to be 18 and more. Or if you have the generalized, the tonic-clonic seizure, the seizures that people fall down and they start shaking, then it's 12 years. And then it's 3 per 4 months. So that's okay, but it has to be this type of seizure for now. So is there then anything that we know that is better than other drugs? Well, there is, for example, it's a nice study already from several years ago that people looked to the best treatment for seizures in these big families or children with neonatal seizures that later then had normal development with, for example, KCNQ2 mutations. And they saw that carbamazepine, it's a specific drug that's also in Spain on the market. I think in Belgium it's called Tigritol. I don't know what the name, I don't remember what it was in Spain. The same. So it seemed to work quite well for most of the children with this disorder. And then later it was also shown that also in children with neonatal seizures and neurodevelopmental problems, so the KCNQ2 encephalopathy children, that it seemed to work often well for the seizures. And why is that? You might remember that potassium channels, they are very important for the firing in the neuron. So actually what happens to make an electric signal in the nerve cells is that here, these sodium channels, they open and sodium goes out of the cell, and then that's the electric signal that starts. And then the potassium channel, it has to block it so that it doesn't keep firing. When you don't have this break, these channels become overactive, and that's exactly what this carbamazepine does. It blocks these overactive sodium channels. So there is a little bit of logic. That we know this, or many people know this, but still, even now, because carbamazepine, it's not a drug, for example, that you can give intravenously. So it was typically not really used a lot in neonates, in children that were in newborn children. And I think in many of the big hospitals now, this is used, but there is still a lack of knowledge. And we're collecting now information on many children and adults with KCNQ2 mutations, and still now we see that some of the children as a newborn, they didn't get this drug, although it works quite well. It's not a miracle drug. It doesn't work for everybody, but it works for seizures for many of them. So that's why I believe we still need to bring this message out, and also there we try to bring the message by collecting information of a lot of people with mutations in KCNQ2. So again, this is it's not a final study, but we looked in 87 individuals with KCNQ2 mutations, and we specifically looked at the mutations of which we know that normally they lead to neurodevelopmental problems. So the KCNQ2 encephalopathy mutation. So we expect, based on the mutations, that children will have a lot of seizures and probably neurodevelopmental problems. And we asked the clinicians and parents, can you tell us what medication you tried in your whole life and what was the effect? It's retrospective, so it's not a perfect study. And we asked them, did the drug make your child seizure-free? Was there less seizures? Didn't it do anything? Or did it even get worse? And I think the first message is there's all these at the bottom, that's all different medications for epilepsy. And you see people try a lot of drugs, and there's not one drug that works for everybody. So that's clear. But maybe here in the first 1, 2, 3, 4, 5 ones, those are all the drugs that block the sodium channels. And I hope you can appreciate that if you use these drugs, there's more children that become seizure-free. Not everybody, bit more. You have more chance to become seizure-free. Here, valproic acid, Depakote, it's also not too bad. But so that's the first thing. And again, we're collecting more information to try to support this more. But the second and maybe even more important question is if we can control the seizures very early, and if we give sodium channel blocker early enough, can we then make sure that children develop better? Will the neurodevelopment also be better? Or is it only working for seizures? And that's an important question. And again, this is preliminary. So I don't think we can conclude anything yet. But from the information that we have now, we divided the children and those that tried a sodium channel blocker drug as carbamazepine in the first 2 months of life. Where's the mouse? Here. And those that only tried it later or even never. And it looks like if you use it early enough, that there are children that do better. Here, this is the degree of intellectual disability, and this is the age at what time they started walking. So it seems like if you started early enough, that children do better. But we do need more information of more children that already tried it or maybe never tried it to compare it, because this might just be a chance finding. But this is a warm request. If people want to participate in this study to collect more information, it might be important to at least get the message out to clinicians to use carbamazepine, for sure for seizures, and maybe also to improve a little bit development. It's not a miracle drug, again. It's not like with using carbamazepine, everything is solved, but at least maybe it can help a bit. So this is a little bit what we know. So depending on what type of mutation you have or the neonatal seizures, or you have mostly developmental problems, sometimes mild, sometimes more severe. And then there's some children that have epilepsy later in life and some not. And we know that the mutation is very important. We've just seen that here, medication, it might also play a role in how children develop, and that's something we try to study. But we think that also our genetics plays a role. We're all different. Blue eyes, brown eyes, but also the way we develop. And we hope that if we can identify factors that influence a little bit how children develop if they have a KCNQ2 mutation, that it also might help us to develop better treatments. And that's why we also have a genetic study going on in our group. I think I maybe talked about it, 2 years ago when I was here. So also here we're still collecting patients, because it's only a study that we can do if we bring a lot of people together. This is all anonymously, so this information will not be shared. It's just to try to help to predict better prognosis and give help other people with the mutation. So this is the email of a student, but you can also mail me if you want to participate. Sure, because we're all mostly talking about this loss of function variants where the channel doesn't work good enough. But I don't know if there's people here that know that their child has a gain of function variant. It's more rare, but then the channel works too much. Are there medication there? This is more difficult. I don't know. Does anybody know whether their child has a gain of function? I see there. Yes. So there is nothing proven. But there are a few drugs that are on the market that we use for other problems, like amitriptyline. It's a drug that is used for depression, headache, neuropathic pain. Donepezil, a drug used for Alzheimer's disease, so normally not used in children, obviously. And guanfacine, a drug that is used for ADHD. All these drugs, they have an effect in the brain, but they also block. We know that it also blocks KCNQ2 a little bit. It's not their primary action, but they also do that. That's known. And then the question is, do they work for these children? It's all medication that normally is not given in little children, so it's not commonly used, except maybe of course, guanfacine, ADHD in children. Well, there is in the last year a little bit of studies on this. There is one group of Israel. They trialed the Alzheimer drug, donepezil, in 4 children. It's not a lot, right? But they had 3 children with KCNQ2, 3 gain-of-function variants, and 1 KCNQ2. And what did they see? First of all, they showed in 4 children, it's not a lot, that it seemed to be safe, even if you give it to children. They had one child, he said he had a bit of problems with micturition, but they decreased the dose and it disappeared. And all the parents of these 4 children, they said their child improved subjectively, in the sense they were more attentive, they participated more, they showed more expressive language or understanding. They also did really cognitive testing before and after the treatment. And in 2 of the 4 children, they said we could measure some kind of improvement in the clinical testing. Mostly, if they do on a scale that measures autism, they showed there was some improvement. But obviously, this is 4 patients, that's not a lot. And it's not a real trial. Normally in your trial, you have a placebo and you treat children with something that's true and something without a placebo, and you see whether there's a difference. This was not the case. So maybe if they would not have given the drugs, maybe they also improved. You don't know that for sure, but it's the beginning. Same for another drug, amitriptyline. Yeah, in Belgium it's called Redomex, but I'm not sure what it's called in Spain. There was one paper already, a publication of one child that tried it with KCNQ2, this variant, a gain-of-function variant. And apparently they did testing, and then also here they saw improvements in attention, communication. But this child, he didn't stop it, the medication or whatsoever. So again, it's not sure it's due to the medication. We now collected data on 11 more children that tried it, not in a formal trial, in different doses. Some had cognitive testing, others not. So we mainly asked retrospectively to the clinician and the parents. We had interview with parents. Did your child improve when he took it? What happened on the EEG, seizures, if there were any, but there was only one child with seizures. What about cognition, mood, behavior, self-care, motor ability, sleep, tiredness? So and actually 9 of the children were said to improve a little bit. Not a miracle, but they improve in at least 2 of these topics. Most parents and physicians said they were more alert, they communicated more. That was the most frequently reported thing. But then 4 of the children of these 9, they stopped it. Not because they didn't support it, but the physician said, we're going to stop it and then check where the effect that we see, it goes away. But it didn't go away. They just stayed functioning the same as during the drug. And then the question is, was this improvement because of the drug? Or was it because they just grow older and develop? Or maybe they could make some improvements and then you stop the drug and it still works. So you see, this is very difficult to evaluate. And there's still, but I have to say that 5 of the children are still on this drug now because the parents and physicians say we think we see improvements. So altogether, there are some drugs that might have some effect, but we're just not totally sure yet. And actually, we applied for funding to try to do some kind of small trials with children that want to try it and parents. Where we start a drug, evaluate it with testing, then stop it for a while, see whether there's differences, start it again, and we received the funding. So if in the future anybody is interesting to try it and interesting to participate in such evaluation, then they're happy to. They can always contact us. And then lastly, I want to give you a little bit an overview of the work of a whole consortium of people of Europe. To make it clear, I don't know of all research on KCNQ2 done in Europe. Probably there's many more people working on it and trying to advance the field, but this is something that we've been doing with this team in the last 3 years. I was coordinating this. There's a group from Italy, Maurizio Tagliatella. He is working on KCNQ2 channels for his whole career. He does this patch clamping in cells to check what mutations do on the current. A partner from Germany that does drug screens, big screening new drugs in a very high throughput manner. Another group from Germany works with tissue from mice. A partner from France who has a mouse that has KCNQ2 encephalopathy. And then last but not least, also Isabella Brambilla, that some people of you might know. She's actually mother of a child with Dravet syndrome and president of the Dravet organization. But she helped us to set up a European KCNQ2 association that tries to connect the different national organizations. I think you might have already had some online meetings to try to see how can within Europe we work together to get things moving and collaborate. So I'm gonna give you very shortly really a summary of what we did. First of all, we tried to develop and test novel analogs, so a little bit changed forms of retigabine. Remember the drug that was taken off the market, sorry. That's one part. But we also wanted to identify new drugs that are already on the market that also activate the KCNQ2 channel, a little bit like I was telling about amitriptyline or donepezil for Alzheimer. And the last, we were also wanted to develop antisense oligonucleotides, ASOs. That's some form of very simple gene therapy that now is more and more developed for several forms of epilepsy. So first of all, we developed in this whole consortium a few models in which we wanted to try to test novel drugs that we wanted to develop. And those were those three things. In my group, we develop stem cells that we generate from blood from patients with KCNQ2 mutations, and we grow them into neurons. So we make nerve cells of it. So from the blood, we can make neurons of people with mutations of KCNQ2. We have a mouse, and Thomas Woodke works with the brain of the mouse. So this is, we take blood, we make stem cells, and these stem cells we grow into neurons. So these are neurons in a dish, and then we put them on like, these are all electrodes, so they measure the electric activity of the neurons. So they can measure whether the neurons become too active or not active enough. And these are, we have both neurons from children with the gain of function and the loss of function mutations. I'm not going to go to explain this all, but this is, if you measure, this is time, and this is all the electrodes, 1,000 electrodes in a dish. And every blue spot, that's an electrical signal. And you can see this is a normal, healthy neuron in a dish, neurons in a dish. They become active, but they also they fire together. So they really start to make a network and they fire together at the same time. Those are the blue lines. So all the 1,000 electrodes, they fire at the same time. And if you look at the neurons of children with the mutations, the loss of function mutations, you get something like this. You see they fire too much. And you can look at a lot of different parameters. And that's what you see here. I'm not going to read them, but you can see how quick do they fire, how long are the bursts, what is the frequency, what is the duration. And you see if it's red, it's more active. It's more than in a healthy neuron. I hope you can see, in general, they become much more active. And sorry. Yeah, if you compare that with the neurons or the networks from patients with the gain of function mutations, you see the opposite. They fire not enough. If you compare this, a healthy neuron, with this, they fire much less, and also these bursts that they fire together, it's much less frequent. So they seem hypo-excitable. So we really have two networks of neuronal cultures that we can measure, and we can measure if we put a drug on it, on this or on this, can we make it more seem like the firing potential of a healthy neuron. So that's our screening system. Sorry. Just 2 words on the mouse. So this is a mouse model that has been developed by my colleague in France. It's one specific mutation that we also see in some patients, this one. And this loss of function mutation, it's been validated in a cell. It's a very gentle mouse that behave quite well. I'm trying to show you. So one of these mice has a mutation in the gene. Yeah. And this is an epileptic seizure in a mouse. So these mice, they do have a mutation and they also have epileptic seizures. You can also test how good their cognition is, and often they do that. They let them swim in a little like swimming pool, and there's one under the water, one place where they can go and sit. It's because they don't like swimming, and they have to learn where it is. And a normal mouse, they really learn where the platform is. If they do this a few times, they find it immediately. But they see that the mice with the mutation, they don't learn that. They keep swimming around, and by accident, sometimes they find the platform. So they have also problems with learning. So this mice, it has a little bit similar, it's very simplified, obviously, symptoms that you also see in children with KCNQ2 mutations. And that's why this is a model that they can use and to study what goes wrong and test drugs also in it. Sorry, I have to check. What they also can see that in these mice, if they make a lot of, like a very high-pitched sound, they can evoke seizures. I think this is probably something specific to the mice. I've never heard that children get seizures because you make a lot of noise, but these mice have it. And that's useful because then they can give a sound and evoke a seizure, but they can also give first a drug and then see whether they can prevent the seizure. So that's an easy way to test drugs. So I'm not going to make this very long. So a first step, one of my colleagues tried to make novel molecules that look a little bit like reticabine, but are stronger and that don't have the side effects of reticabine. And this is one of them. This is reticabine, the chemical structure. It looks a little bit like it. It also activates the current. They tested it in mouse models with epilepsy, and it seemed to work for epilepsy in general. It goes to the brain because that's also important. And you only have to give it once a day. Reticabine, you had to give it 3 times a day. No details, but we put this drug on our cultures. Remember, they fire too much, and all the different mutations that we have of children with KCNQ2 mutations, you see if you put reticabine on it or you put this compound on it, reticabine analog, compound 60 we call it, you can reduce this hyperactivity. And the higher the dose you give, the more quiet the neurons become. And we can revert this if we add a drug that opens the channel again. So it seemed to work in our neurons, even in the neurons of children with mutations. So then our colleague from France, he tried it in the mouse model. So they give the drug through they inject it in the gastrointestinal system. They give the sound, the high-pitched sound, and they look whether they have seizures or not. And what did I see? I'm going to explain these graphs. This is increasing doses of the drug, and the more drug you give, the higher and the more intense the sound needs to be before you have a seizure. And also, the number of mouse that have seizures declines. And so some of the mouse, they don't have seizures anymore if you give this drug. And he's now testing this drug and giving it chronically to see whether it improves the cognition. Testing the swimming in the little swimming pool of the mice. This is ongoing. But obviously, this is a new drug. It takes a lot of time for safety and develop it before you can give it to patients. And it's also often millions of development. We really need companies to help us to develop a new drug. So one of the other things that we try to do is to screen drugs that are already on the market or proven to be safe and see whether they also can activate the channel. So this is a work from a collaborator from Germany. They took 5,600 drugs in different stages of development. So these were already on the market and these were tried in clinical trials. And they put them in a screening system to check which of these 5,600 drugs they activated the channel, the KCNQ2 channel. These are all the compounds. Most of them did not do anything, but a few of them, like retigabine, which was also in this library, they activated the channel. And one of them was C4, compound 4, we call it, so we give it a name. It was a drug that was developed for another neurological disorder. It was safe. It was used in humans, in adults, but it was safe. It caused no serious side effects. There were several clinical trials. So this is a very interesting drug. So we tried to test it further. Without going into details, I first tried it in mouse with epilepsy, other forms of epilepsy. And I'm not going to talk about the details, but it was just as effective as retigabine to block seizures or to prevent seizures in mice with epilepsy. But this is not KCNQ2, right? So that's the next thing we tried to do. We tried, if we put this on our neurons in a dish, we can see this is just looking at one single neuron. They give electrical signals. You put the drug on it, and it fires less, and then you add a channel, a compound that opens the channel again, and it starts firing again. And then in our cultures with mutations of KCNQ2, these are cultures, neuronal cultures without mutations, and with the mutation you see if you put retigabine or the drug on it, it reduces the firing and this hyperexcitability of the drug. So this seems a promising compound that has been tested in humans, so there is safety data. The problem with the drug, it is not on the market. You cannot buy it in the pharmacy. And that's because the company that developed it, they stopped the development. They did a lot of clinical trials, but they said, it's not so much more efficient for this other disorder that they're testing it for than the other drugs. We're not going to put money in it anymore. So for the last more than a half year, we're trying to contact the company and ask them that they can give us more information. For example, what is the safety? How quickly is it metabolized? How often do you have to give it? How do you make it? So that if we see that everything seems safe and well, we can really ourselves ask for funding to start a trial directly in children with KCNQ2 related disorders. I have to say we're supported by 2 European institutions that help to get repurposed drugs to people with rare disorders, but the discussions with the company are not straightforward. We are now going up to the CEO, and we hope that they are more willing to collaborate or help us. And if not, we might start a media campaign or something to try to get the information. So we might get back to you to get some help. And I think just the last maybe 2 slides. So one thing that we also try to do, you might have heard of antisense oligonucleotide therapies. For example, if you follow a little bit Dravet syndrome, also a very severe form of epilepsy with neurodevelopmental problems, they have a clinical trial with it's not a real gene therapy, but it looks a bit like it. So it's actually this. So you have your DNA, where the mutation is, and it's first transcribed to something we call messenger RNA, and then the protein. In this case, the potassium channel is made. And traditional drugs like retigabine, they act on the protein. But what antisense oligonucleotides do is they interfere with this stage, the mRNA, and they can, for example, break down this RNA so that this disease protein is not made. That's the idea of antisense oligonucleotides. So we hypothesize that for gain-of-function patients with gain-of-function mutations, if we can reduce the number of copies of KCNQ2, this might be a potential therapy for those. So we tried a lot of and we designed a lot of these antisense oligonucleotides, did a lot of experiments, and just show you one graph. I showed you these nerve cells. They're not so excitable. They are less active. That's the blue one. If you give them the ASO we developed, the purple one, they act a little bit like the green one, the healthy neurons. So this is the first step, because this is in a dish, right? So we're not there yet. We're not there at the stage that we say, okay, we give this to children. As I said, what we're doing now, we're trying to contact this one company for this compound 4, and we're finishing some safety studies in a dish for the antisense oligonucleotides, and applying for funding to test the safety in mice, and asking also, trying to contact companies to raise their interest to collaborate with us to really develop this further. And then I think a last few slides. So I already talked about this funding. So this is future work. The work of this one consortium, it ended. We got funding from a new consortium. We just got this message 2 weeks ago. There's one little hurdle, that there's an Israeli partner in it, so we have to ask the permission of our university to collaborate, which is not a trivial thing apparently. But what we want to do is that first there is a group, the Israeli person also, to try to improve variant prediction, to say this is a loss of function mutation, this is a severe loss of function, a gain of function, to predict what the mutation does, because sometimes it's still difficult. We want to identify other drugs that might not specifically work on the KCNQ2 channel, but maybe on other channels, and we use transcriptome RNA sequencing and try to, on other pathways that might go wrong. There will be people working on EEG biomarkers, so they will test whether changes in EEG can predict how they will develop or what the effect of specific drugs is. So we will try to analyze a lot of EEG data from children with KCNQ2. And then last but not least, as I said, these trials of donepezil, amitriptyline in children with gain-of-function mutations, but also cannabidiol. Cannabidiol, a drug that's, I think, on the market also for epilepsy in Spain. It is known to also activate Kv7 a little bit, but we don't know whether it works better for the seizures or even for development in children with KCNQ2 mutation, because it's little or not used. So that's something that we also want to try. So feel free to reach out. Just a last slide, that there is a book with a collaboration of a lot of people, also from the American KCNQ2 cure. There's a QR code on the next slide. It's in English, but it's a big booklet that tells all the fundamentals about these disorders, and also stories of a lot of parents of children with these disorders. So trying to explain what problems they face. And these are the people from my team or from the European consortium that I greatly want to thank, together obviously with all the families and parents contributing to the work. Thank you. Lo siento que es en inglés. Si hay preguntas en español.
Para mí, no tengo claro si los mismos medicamentos que sirven para cerrar el canal de potasio en amigo. He visto en las diapositivas que hay diferentes, pero no tengo claro que los doctores, los médicos ahora distingan mucho. Por lo menos yo sé que hay ganancia o pérdida en el canal de potasio porque lo he visto en estas charlas, pero realmente cuando voy al médico ellos no me dicen si es una ganancia o es una pérdida. Entonces tengo dudas de si se aplica apropiadamente el tratamiento. En mi caso, que creo que es una ganancia, está con carbamazepina, que creo que por lo que he visto es un poco así.
Yeah.
Por eso.
I'm gonna, because it's not a straightforward answer, so I'm gonna do it in English. I'm sorry. That's a very good question, and I think part of it is that especially for the gain of function. No, I'm gonna start differently. We think if we really want to act on the potassium channel, that the treatment should probably be very different. That you need the blockers for the gain of function mutations and the activators for the loss of function mutation, retigabine or maybe amitriptyline or donepezil. For the medications that work for seizures, we're not so sure yet, because we know that, or we think we know that carbamazepine, it seems to work well for seizures in loss of function mutations, but I know that there's children with gain of function mutations that also respond well to carbamazepine. So it's not. So it doesn't seem to be like there that's really an opposite effect. We're not sure yet. Probably because the seizures in children with gain of function mutation, it's probably an adaptation of the brain. It's not totally directly from the potassium channel problem. It's all, yeah. So it's all, if a gain, yeah. Let me say it this way. We don't have evidence that it's bad for gain of function mutation. It's also a sodium channel blocker. But for now, we don't have, but maybe our study can show us more. We don't have the impression that sodium channel blockers are bad for children with gain of function mutations until now. So lacosamide is a sodium channel blocker. It seems to be okay. If it works for your individual child, you have to check whether it works, obviously. And if it doesn't work, then discuss with the your medical doctor to stop it again. But it doesn't seem to make things worse. That's no, yeah.
¿Quiere decir que con la medicación puede llegar a cerrarse el canal de potasio o no?
In the mutations that work too well, too good, the gain of function mutations, there are medications that can block it a little bit. Yeah. We don't want them to block totally because that's too much. But with a specific dose, the aim would be to block it a little bit more. And the other way around, for children with loss of function mutations, we want to open it a little bit more. It doesn't have to be always open, but a little bit more. And that's what these drugs do.
Lo que hace es bloquear, pero que no tiene por qué bloquearlo totalmente. Pero está hablando, claro, en el caso de mi hijo, sí, que le he preguntado porque era una ganancia en el canal de potasio. Primero le he preguntado por la carbamazepina y luego por la cosamida, que es lo que realmente está tomando mi hijo ahora. Entonces, pueden cerrar el canal de potasio, pero no asegura que lo vaya a cerrar totalmente. ¿Vale? Y también lo que me ha dicho antes, que realmente tampoco el hecho de que esté tomando una cosa u otra puede tener un efecto negativo. Aunque mi hijo tenga una ganancia en el canal de potasio y probablemente cualquiera de los dos puede, bueno, realmente la cosamida mejor, pero que realmente no tiene por qué tener efectos contrarios el que esté utilizando una cosa o la otra si tiene una ganancia en el canal de potasio. Más o menos.
Por lo que veo, los tratamientos son diferentes si es ganancia o pérdida. Pero yo no tengo claro, o no sé muy bien, por lo menos los doctores en nuestro caso no nos han sabido decir si la mutación que tiene nuestro hijo es de pérdida o de ganancia. Yo no sé en el caso de los demás si lo sabéis o no. O si es algo que es posible saberlo o es imposible saberlo, no sé cómo.
Sometimes it can help. Sometimes the specific mutations have been studied and we know it's gain or loss of function mutations. Sometimes it really helps to look at the clinical history of your child or to look at other people that have the same variant. And if you want, I can check whether we know of other children with this variant and whether it has been studied. So I'm happy to check the specific variants. Sometimes it still remains a doubt, but I can try to see whether we can figure it out if you want.
Hace 2 años lo que hicimos fue que nos escribíais un email, nosotros lo pasábamos con una serie de datos que tendréis en vuestros informes donde os dieron...
Sí, del informe genético.
Eso es. Y pasamos toda esa información y te dicen si está descrito para vuestra mutación, si es de ganancia o pérdida. Hay algunos que no están...
Si se han estudiado.
Si se han estudiado.
Sí, nosotros...
¿Nos lo pasáis? Sí, lo pasáis.
Vale. Aquí lo vieron los médicos de genética de este hospital, miraron, pero no tenían evidencia de si era pérdida o ganancia. Entonces, no sé si hay alguna forma de...
Generalmente lo comentamos a la genetista lo busca y si no, algunos pacientes se los hemos mandado también a Sara, siempre de acuerdo con los padres, pidiendo autorización.
sometimes I indeed know of other children because parents contacted me or that are not, the geneticists don't see it in the literature, but sometimes I know of more children than what the geneticist can find in.
Do we contact directly to you or through the association?
Like you wish, it's the same. Maybe right. Yeah. I thought I had my email somewhere, or you can really distribute it. That's okay. I'm happy to check our comments.
Martina es también como Lucas, es como la variante que está alterado la parte derecha del gen, que es como severo. Y al año ya se controlaron las crisis, la epilepsia se controló y ya el electro bien. Y nos dijo el doctor como que la epilepsia había sido como síntoma, pero que la causa es el síndrome, ¿no? La alteración genética. Entonces está tomando antiepilépticos, pero no tiene epilepsia y vemos que ella no es que haya una mejoría importante. Entonces, claro, esta medicación que es para la epilepsia, porque ella epilepsia no tiene.
No tiene más, ya no tiene. That's a good question. The question is, how long do children that are seizure free, because we see a lot of children don't have seizures anymore. I know of several children that stop the medication and don't have seizures again. But it's not guaranteed. There's some children that later in life they start to have seizures again. In general, it's not that bad as in the beginning. Sometimes only with fever, or in periods with a lot of emotional, so in general, if they then restart medication, they're very well treated. So it's not a guarantee, and this is two aspects that you have to balance a little bit in the discussion with your medical doctor. Like, do we take the risk and we take off the medications and we see what happens? Or do we go for security and we say, oh, it has been so difficult years before, we continue it still because my child doesn't have any side effects. If you think they have side effects or you have the impression, in discussion with your medical doctor, it might be worth trying to at least taper. But realize that you have to see whether seizures not recur. Some people can stop seizures, medication, but just not everybody.
Casi todas las medicaciones que se están probando y casi todos los estudios es, en mi opinión, y creo que la de todos, para tratar de controlar la epilepsia. Pero lo que la mayoría espera o esperamos es tal vez algo para, no sé si curar, porque no sé si es la palabra apropiada, ¿no? Pero para disminuir los síntomas que tiene la mutación en los niños o las niñas. No sé si en ese sentido la terapia génica o algún otro tipo de medicación o de terapia o tratamiento que se esté estudiando puede dar alguna esperanza cierta, digamos, en esa línea.
Yeah, I think that's a good question, because that's at the end the goal is for many children with epilepsy and neurodevelopmental problems, but surely for children with KCNQ2 related disorders, because many of your children will not have seizures, I think. And I think the goal, or the whole discussion that I do here, we hope that by influencing the channel, so take really the cause, that it will not only treat seizures if they are there, but also improve development with the drug or with the gene therapy. That's the goal. The question remains to what extent we can still do that, because the gene is there from even in the belly, already from fetus. But I do strongly believe that at least we might be able to improve development. Maybe not cure, but improve. But that's the goal. The difficult,
Es que al final la meta, aunque lo que están tratando es esto de la epilepsia, al final la meta final es tratar de buscar que estas medicaciones o estos tratamientos, bien sean, bueno, no ha dicho químicos, pero los químicos que entendemos, también las terapias génicas, al final traten de mejorar el desarrollo de los niños, o sea, no solo el tratamiento específico de la epilepsia.
Gracias.
That said, it is true that it's more difficult to get big pharmaceutical companies interested in trials for neurodevelopment, because seizures is easier to measure. They go away and you see it, the drug works and it gets approved, it goes to the market. To measure improvement, you need longer time and you need a good comparison. And that's where I think, and I understand that in Spain you're thinking about a registry, a natural history study maybe. That will also become important to really say to companies or academics that try drugs, like, this is how normally children develop, and we have this information. If you try a drug, you can compare it with children that did not use your drug. So that will be really important. Yeah.
¿Hay algún tipo de estudio en relación con las células madre relacionadas al cáncer?
To like transplant them in the brain, they mean, or?
Bueno, yo creo que tampoco se centra solo en eso. Si realmente algo que se está trabajando con células madre, porque no es relativo al cerebro, ¿no? La implantación de células madre en el cerebro, ¿no? Sino en general, ¿no? Que
yeah.
En general.
Okay, so in general, because we use células madres from that we get out of the blood from children with KCNQ2 mutations to grow them in the dish to study the nerve cells. We make nerve cells of them and we study it. For now, there's not such a thing to transplant them, for example, in the brain, because the problem for KCNQ2 is that it's all over the brain, and it's until now it's impossible to make a whole new brain with healthy neurons. Yeah, we grow them in the laboratory to study what goes wrong in the nerve cells of children with mutations. Okay, muchas gracias.